Solving exponential equations. In all honesty, this is the main reason for logarithms. But you don't always need them. And everybody starts seeing a problem like this. They see a variable in the exponent, and they think that a logarithm has to be used. You only need to use a logarithm if you can't basically get the bases the same, because you've solved the problem just like this earlier in this chapter. You look at those two sides, you got a 9 as a base and a 27 as the base. I can actually get the two sides the same. And if you can, you don't have to use a logarithm. Can you if you just absolutely love them? Yes, you can. Okay? But in this case, it's probably not going to be as accurate as if you actually just manipulate the problem. Because when you use logarithms, sometimes you have to round. Okay? It's only going to be so good. And so they might not be as good as if you said, well, 9 is 3 squared, which is to the 2p power. And that's 3 to the third, which is 27, to the p minus 1 power. Now, I wrote it like this again because it's been a while since we've looked at one like this, because we've been dealing with, logarithmic form and exponential form and natural log, so it's been a while. But right here, it's a power to a power. It only has one base there. And so what do you do with exponents? Multiply, and 2 times 2p is 4p. And this is where a lot of people will make a mistake, is when you multiply this, you have to distribute that 3. So it's kind of like, you can maybe look at it as like that. So it's going to be 3p minus 3. Very good. You can obviously see if you put minus 1, that's going to change your answer. The nice thing about this one is now those bases are the same. So whatever I put in there for p, I also have to put in here, right? And for this to actually end up being equals, I better have the same exponent here because the base is the same. Right? That's the only way it's actually going to work out. And that's the beauty of these, because then really that base has no significance to the problem anymore. I know because the bases are the same, the exponents also need to be the same in this case. Now please realize this won't always happen, but when it does, I want you to notice it. It should save you plenty of time. So now I have turned this very complicated exponential equation into a very simple algebraic equation that you've solved since maybe 7th, 8th grade, or maybe Algebra 1, depending on what you had. So you subtract 3p from both sides, and in fact this one solves quite easily. P is negative 3. Now some of you might be hesitant because I always told you can't take the log of a negative. Well, I'm not saying I'm taking the log of a negative here, right? I'm just saying that the only value for p that's going to work here is if I put negative 3 back into the original. Obviously, that's something you could check if you really felt like it. You put negative 3 there, you could put negative 3 there, and find out, do both sides give me the exact same thing? They do, if you really want to know. So that one's pretty straightforward. What do you notice as being most definitely different on this one? Yeah, 42 doesn't have an exponent, so we would think this one would be easier, right? There's only one exponent. But the one thing I can't do in this problem is get the bases the same. I could in the last one. That was very nice. I mean, unless you know exactly 6 to what power gives you 42, that's going to be the only way you're going to do this, right? So, unfortunately, we're not really going to be allowed to solve this one the way we'd like. Okay? And so what we're going to do is try and take that variable that right now is in the exponent, we're going to try and get it out. We're going to try and get it back down to the level we're used to working with it. And there's only one way to do that. A logarithm. And there are certain logarithms you can choose. I would strongly recommend you choose a logarithm. You could just log base whatever you want. Log base 17 if you felt like it. But we should probably use one of the log bases that are actually on our calculator. And there's 2 of them on there, right? Log base 10 is on there, and log base E. Very good. I was trying to trick you there. But log base E is on there. It's known as lateral log, right? But log base 10 is also on there. And didn't we just deal with that today when we were correcting your other worksheet? So let's go with log base 10. It's called the common logarithm, so it would make sense to do that. So as in algebra, if you do something to one side of the equal sign, you must do the exact same thing to the other side. So I have taken the common log of both sides. How can you tell that that's the common log? Yeah, I didn't write a base, right? And if there's no base written, it's understood to be 10. And so, yeah, you already told me that we know that that's a common log because it's understood to be there. Well, the beautiful part is that one property we learned allowed us to take the exponent and get it out of there, right? That's what that one rule told us we could do with any logarithm. And so that's exactly what we're going to do. But what operation then ends up here? Times, right? Yep. And here's again where people get a little nervous. Log base 6, is that a variable? Is that going to vary from problem to problem? No, log base 6 is a number. Do we know that right off the top of our head? No. Log base 42, is that going to vary from problem to problem? No, log base 42, if that's in another problem, it's still going to be the same number. But it's not a very nice number that we just know off the top of our head, right? If we were to find both of these right now, we could go to our calculator and do that, right? But we would have to round both of them at this point, right? So how about we make rounding as easy as possible? And when you do algebra, our main goal is to get x by itself. We have now moved it out front, but is it by itself? Not yet. So let's get that log 6 out of here. Log of 6 and log of 6. If you divide, it's still just 1. That may be the new winner for the weirdest form of 1 we've used. Okay, but it's still 1. So x is going to equal whatever that is. Well, didn't we just type stuff like that into our calculator? Well, let's do that. Then I don't have to round until the very end. Let's do that. So it's log of 42 divided by log of 6. You once again have to be very careful about those parentheses. Has everybody got that written down? So I can go to the calculator? All right. So here we're going to go log, because that's the log we chose, right? 42. Remember, I closed it off right there, divided by log of 6, right? That was the number. And some people think this is 7, right? Not even close, because 6 to the 7th power, I hope you understand, is very, very large. What do you think? 6 to what power? I know some of you already hit enter, but 2, because 6 to the 2nd is 36, and 6 to the 3rd gets pretty big in a hurry, right? So it's going to be right around 2 somewhere. So does it say in the directions where to round? No. Well, let's go out. I think it's very safe to go out to 4 decimal places. So 2.0860. And again, that's where you have to step back. And what most people can't do is answer the question, is that believable? Most people can type stuff in very well. And let me show you the biggest mistake that students would make from another school and not know that it's wrong. And I hit that way too many times. You think it would be very easy to make that mistake? Are you taking the log of the same thing anymore? Not even close. Is that believable? 6 to that power being 42? Not believable. That's not one of those extreme cases where it'd be like 100 or something, but that would be something you could feasibly write down because it doesn't shock you. But it has no way of being right. Okay? So watch out for those. Now, this may annoy you a little bit, but I had to prove to you that what you were just doing on 10-5 worksheet on the back actually works. Because this is the algebra you would do. If you remember from, and I'm just throwing markers apparently. If you remember, this is exponential form. Can you rewrite that in logarithmic form for me? Log base 6 of 42 equals, isn't that what I just told you to do on that homework assignment? Take log of that one there and divide by log of that one. That's what I just told you to do. That's why it works. Okay? You could have just believed me, but now you know why it works. And if you ever get really stuck, you could always just go back and do the problem this way. Unfortunately, though, this problem can't just switch it around like that, right? This last problem, you could switch it around because, like as somebody mentioned, there was no exponent on that 42, so it made it a little easier. This one, a little bit harder. We have a variable in the exponent. We'd like to get it out of the exponent. One way to do that is to get the bases the same. It's possible, but highly unlikely. 8 and 5? I don't think so. So we have to get the exponent down some other way, and there is only one way, using a logarithm. And let's stick with the common log. So I have taken the common log of both sides, so I have kept everything proper. I have not changed any values. It just looks a whole lot different. Please keep in mind the whole reason for doing that is because now that and that can be brought out front of their respective logarithms. Okay? And so this one really says 2x minus 5 times the log of 8, which is just some number, okay, equals x plus 1 times log of 5. Are there any questions how I got to where I'm at right now in the red? No? Log of 8 is some number. Log of 5, some number, neither of which are nice. So we have a choice to make. Either I go find what log of 8 is and take that really not nice decimal and distribute it to 2x minus 5, and then go find log of 5, again a not nice decimal, and distribute that to x plus 1. That's one option. Another option is to move one of those logarithms so I only have to distribute a really not nice decimal one time instead of twice. I'm hoping you're going to go with just distribute a not nice decimal once. And normally there's a better way to move it. Would you rather distribute to 2x minus 5 or distribute through x plus 1? I think x plus 1 is the obvious choice, right? Which means I have to move which one? Do I move the log base 8 or the log of 8 or the log of 5? Which one should I move if I only want to distribute through x plus 1? That's the tricky part. You have to look ahead. Which one should I move? What's that? Well, we'll leave the x plus 1. Let's move one of the logs. Log 8 you want to move? Log 5 you want to move? Yeah, move log 8. Because if you divide by log 8, what happens on the left side? They cancel. So do I have to distribute anything through 2x minus 5 then? Well, I could distribute a 1 if you want me to, but you know. And then you divide by log base 8 over here. Will I have to find out what that horrible decimal is? Yeah. But then I can distribute it through x plus 1. Well, that's much easier, I'd say. Right? So right now, let's just clean this up before we move on. We've got 2x minus 5 equaling something over here, right? I'm going to write x plus 1 down, and then I'm going to write our horrible decimal right there once we find out what it is. And we will round to 4 decimal places. We will count that as good enough. Unless you really want me to keep this in my calculator and go a long distance, I don't think we need to do that in here. We'll save that for another day. Log, I believe it was of 5, right? Is the way we decided to move. And then divided by, once again, keep care of your parentheses. I believe that is what we chose to do. Is that correct? All right. And hopefully that is the number that you got when you hit enter. And did I say what, 4? Is that what I said? So it's 0.7740, right? Very good, 0.7740. Are there any questions how I got to that number? No? So that number is what goes right here, right? Agree with me? I just put a blank there. I don't really need the blank. So are there any questions where we're at so far in this problem? Well, now you unfortunately do have to distribute that relatively unpleasant decimal. So 2x minus 5 equals 0.7740, if you want to leave it on there, x, plus 0.7740. I will be quite blunt and honest. I'm surprised how many people all of a sudden are unable to do regular algebra when there is a decimal involved. It's rather amazing. Yeah, exactly. Let's just get the x's together, right? Isn't that what you normally do? So let's, as somebody just told me, let's subtract the 0.7740x over to the other side. That's the same thing you would have done otherwise. What do you get? 226, right? But what's on there? Very important that's on there. X, very good. A minus 5 still, right? Equals 0.7740. I was slightly disappointed when I heard so many calculators going for 2 minus 0.774, but that's all right. I'm hoping that the calculators will not be going when you add 5 to the other side. Add 5, add 5. Hope that was okay that I cheated just a little bit there and just threw the 5 in there, right? Because that's what it would be. Well, now that just looks horrible. Well, now what? Divide what? Yeah. See, just because there's decimals there, it doesn't really change what you do, but it's just amazing how many people all of a sudden, they just, algebra is a foreign concept. And what do you get? 47096. Now, checking feasibility is a whole lot harder when you get a problem like this. But you can still kind of somewhat look at it and say, what do you think? This is about 5, right? Give or take a little bit. I think we can at least go back and say, does this even seem possible? Because sometimes you'll get an answer that isn't even close. So we're about 5, right? So if I was to put about 5 back in the original here, it would be 2 times 5 is 10, minus 5 is about 5. So 8 to the 5th on that side, right? Big number, right? Over here, if we put 5 in, we're saying 5 to the 6th, right? 5 to the 6th, 8 to the 5th. Do you think they have a chance of being relatively close to each other? They probably do, right? And you obviously you could put that 4.7096 in there. Is it going to be perfect if you put 4.7096 in there? Will it be perfect if I do that? No, why not? Because we round it. But it's going to be close if you put 4.7096 in there. Okay. It's at least believable. If one side was 8 to the 12th and the other side was 5 to the 3rd, we obviously have a problem. Right? But that's stuff that people just keep right on going and they don't even realize that can't even possibly be right. Okay? So what I would like you to do right now, if you have not already done so, is try that one right there on your own so that you get some confidence built up or find where you're possibly going to make mistakes. Okay? So go ahead, give it a shot. All right. Now here's what I want you to be able to do, at least at some point. So your attention up here, please. I want you to be able to kind of start looking at these and at least have a general idea of where this answer is probably going to be. And you can easily do that by just kind of substituting in some values and seeing if you think it's believable. For example, I do think it's going to be around 0. If I do that, that means it'd be 2 to the 3rd equals 3 to the 0, which is 1. Does that seem believable? Are those two really close? Not really, but they're not really far away either, are they? 0 and 8, that's not too bad, right? Well, what if it was 1? This would be 2 to the 5th and 3 to the 3rd. Those aren't too far apart either, are they? So it's believable this will be around 1 somewhere if you actually put that value back in. But unfortunately, we can't get the bases the same. So common log. Which allows you to do that. Don't just start looking at these problems, start going, oh, it just goes here, that just, no, now without a logarithm it doesn't. You can't just start moving things around. So here we've got 2x plus 3. I'm hoping it was an obvious choice of which way to move things this time. Maybe not, but here we have to distribute a horrible decimal. Here, there's really no distributing, you just have to multiply, right? So you just go with the multiplying, that's what I would do. Divide by log of 2, cancel, so it's 2x plus 3 equals 3x times some horrible decimal, right? And according to mine, that horrible decimal was, yeah, and so then you take that times the 3, and you get like 4.755, right? If you do basically all of that, right? 4.755x. But again, I just went around, somebody missed that x. That's so easy to do. When you have all these decimals, you're not used to having an x at the end of that thing, right? So watch out for that. And so you subtract 2x. So 3 equal, again, I hope you didn't use a calculator on that one. Right? And divide, it keeps getting smaller. Divide by 2.755. Right? So 3 over 2.755. And I got 1.0889 approximately. Okay. Are there any questions? Any questions why we use a logarithm to do it? It's either that or guess and check, which, as you can imagine, could take a while with some of these. All right. On the back, I'm going to give you the 3 problems you will be responsible for tomorrow. I will just come around and kind of see how you did on them. So number 1. And what I want you to do on all of these is obviously solve. And then what I want you to do is check your answer, which means put your answer back into the problem and see how close it is. More than likely, it won't be perfect because we are rounding in most cases. There's number 1. Number 2. It could be.